Yeah, welcome, and thanks for listening to this talk of our paper presentation for an experimental evaluation of process concept drift detection at VLDB 2023. I'm Niklas Adam, and this is the joint work with my co-authors Cameron Pitch, Tobias Wolkoff, and Will van der Aal. So the problem we are tackling is a concept drift in processes, and more specifically in the data-driven analysis of processes. So this is called process mining. And the situation that we have is we start with a process. So there in real life, somewhere there is some process being executed. It could be in business, could be in healthcare, and so on. And this process that is executed generates event data over time. And we can then actually use this event data to analyze and optimize the process that exists in real life. And such applications of analysis could be discovering the process. So actually, we don't know how the process looks in real life. We might have an idea how it should look like or how it could look like, but we don't know for sure. So what we can do is we can apply process discovery algorithms to find the real life models of processes. We can also apply conformance checking algorithms. That means we have some rules of how the process should be, and then we analyze whether the actual execution of the process conforms to these rules. And we could use operational support methods like predictive process monitoring, where we have looked at the past event data to find out what are the rules, what are like typical patterns that we can observe in event data and during the execution of the process that we then use to predict during the execution of the process what will happen next, or we could even make a recommendation what should happen next. And now, like a very, very common problem that we always face in reality is concept drift. So you can just imagine there is some type of new legislation. There are some big shifts in the global like economy or how we live, as it has been several times over the last few years. And if there is such a concept drift, that means the process changes the underlying process. And that also means that kind of like the rules we have learned in the past, like for example in predictive monitoring, they might not be valid anymore, or the models, how we have discovered them in the past, they are not valid anymore. So we actually need to kind of deal with that, because if we don't deal with it, like our discovered process models will be less accurate, the operational support we provide will be less valuable, and so on. So what we need to do is we need to discover when does a process change so that we can deal with that. For example, by relearning a model, by discounting past value, and so on, past knowledge, and so on. Now, this sounds, in theory, it sounds easy. You just look at the process and you see when does it change, and then I will just update with whatever strategy I decided to update my models with. But actually, it's not that easy, right? Like we can't see the real process. Like there is some process going on somewhere, but we can't, it's not tangible. We cannot see it. We cannot see its rules. The only thing that we can see is the event data that this process generates. So actually where we have to look at is we have to look into the event data to then find out whether this process has changed, and maybe also how did it change. And this is the problem of process concept drift detection. And like we start from this event log that we have. And in event log, we have different events, as the name already says, and every event is associated to one execution of the process, which is a so-called case, an activity, and a time when this happens. And then there can be also additional attributes for that. And typically we have like three different, or we can have three different areas of techniques how to detect such process concept drift. Now, I adopted here the names that are quite common, like in the general area of data mining and machine learning. We have made like a slightly different taxonomy, and you can dive deep into that. It also goes like on different areas of granularity. You can dive into that in the paper. We just made it here for a simplification reason. And in general, there are three different areas of algorithms. The first one is distribution-based techniques. So you look at the event log over time. You take, for example, your events from the last month, your process executions, your cases from the last month, and then you derive some distributions and check whether they are the same. And if they are not, you classify a concept drift between this last month and the last month before that. Then you can also do something that's called error-based techniques. So here you look at the models that you have learned, and then you look at the model's performance over time. And if it degrades, then you know that your model is not as accurate on the newer data anymore, and there might have been a concept drift, and then you like classify this point in time as a concept drift. And then there are also techniques that are typically called multiple hypothesis testing. This is something that's so far not that prevalent in process mining, and we will come back to that in the end in our conclusion. But here you basically just perform multiple hypothesis tests and then take the majority vote of that. So if we now look at all of the process concept drift detection techniques and like that we have introduced so far, because we would, for example, would like to know what is now the best technique to apply in our scenario, or what is the best technique to further develop, then we would typically would like to see some evaluation goals, right? We would like to see that evaluated for this, and this. And for this, we collected like some like typical evaluation goals for process concept drift. And we will now quickly go through them and then see actually that almost none of the papers uses all of these evaluation goals. And this is also one core part of the motivation of this framework, that we can apply that to all of the techniques. So first of all, we have our detected concept drift, and we have our ground truth concept drift. So like in this scenario now, we know which concept drifts there are. We also know that there are kind of different types, and we will later see what that means. And we know what kind of predictions of which concept drifts our process concept drift detection technique has given us. So the first thing we now do is we need to assign like true positive and false positive in here. So what we do for this is we define an acceptable lag window. So we say like a detected concept drift should be within, I don't know, 7 days, 1 day of the original, of the ground truth concept drift. And then we look at this acceptable lag window, but it still could be the case that there are multiple drifts detected. And what we say now is that there can always be just one of these detected drifts that corresponds to the ground truth drift. So what we do is some bipartite matching, and even if there is a second detected drift within the window, it's now a false positive. And we have actually done some sensitivity analysis to that, where we just say all of them are like true positives, but you can read that in the paper. And now we have basically our true positives, our false positives, and what we do now is we calculate like the accuracy of our of the corresponding concept drift detection technique based on this. And this is just like one of the most simple things you can do. What we are then also interested in is the latency of the technique. So it could be the case that some of the techniques are much further off the actual ground truth drift, and there's like a systematic delay in which they detect the ground truth drift. So this is what we would like to quantify with the latency. We look at the time difference between like the detected and the ground truth drift based on our bipartite matching. And then, and this is, and we will see later some examples of this, like the concept drifts in processes are of different types. So there can be different changes in a process that result in a concept drift. And what we would actually like to know, and ideally what we would like a good process concept drift detection technique to have, is a high versatility. That means it can detect all kinds of different changes in the process well. And for this, we can look at the different types of changes that we have. And then for all of them, we calculate how many of those could actually have been detected. We can also just quantify it in this direction, because we don't have the other direction. We don't know what a detected detected concept drift of which type that is, because we only detect drifts and not the type of them. And then additionally to that, first there was the quality of the results, but we also have some evaluation goals with respect to the quality of the algorithm, which is the scalability, which is I think quite self-explanatory. Then we want to know how sensitive the algorithm is to choosing parameters, and also how robust the algorithm is to noise in the data, because that's what we have quite often. We then collected all of the process concept detection techniques and classified which techniques evaluate which of these evaluation goals. And actually, it's only 3 techniques that are evaluated for all of those out of I think 26 techniques. So that means that actually right now there's not really a comparability between the most or all of the techniques. So that's what we would like to have. We then grouped all of these techniques according to our taxonomy. So you can think a bit, the feature-centric is kind of like what's often the distribution-based techniques, and the feature-based descriptions what's often the error-based techniques. And then there are like different scopes of which process features are extracted, and we grouped that and looked at where the implementation are publicly available such that we can check our implementation. And then we selected like a subset of techniques that we would re-implement all in Python so that there is a comparability for the scalability. And we ended up with this selection of techniques. Then we looked at which data sets are employed, and we pooled all of the ones that we could use together. And we ended up with a data set of 4.5 million events and 132 concept drifts. And now we come to the change types, and this is 16 different change types. They are quite equally distributed among the data sets, so there's no like systematic skew toward one change type. And you can see here some examples. So for example, the first change type on the top left here, it's just making an activity skippable or not. So you can skip a step in your process or you cannot skip it. And there are many other change types here, and you can take a look into them. Now we come to the results for the techniques that we have chosen. First of all, we have like our accuracy results, and here we have the precision and the recall and the F1 score. And actually, we have one technique that's performing very well, which is what we call RINS, and also the EMD technique. It's the Earth Mover System technique that is performing quite well. But let's move on with that. For the latency, we also have that some of the techniques are performing quite well and others tend to have a high latency, but that also often has some like effects with the acceptable lag window that you have chosen. The higher you choose the acceptable lag window, the better the accuracy gets, but the worse the latency gets. And then, and this is, I think, one of the most important plots, is the versatility. So here we can see which techniques have kind of like systematic weaknesses when it comes to certain change types or certain types of change types. And actually see there is only one technique that can detect all of these types. This is EMD, Earth Mover Distance, and there are like some techniques that have quite the issues with other types. The underlying reason for that could be that the Earth Mover Distance actually takes the variance of the process executions, which is the end-to-end execution of the process in terms of activities, and then compares the distributions in like subsequent time windows. So actually like this, all of the different changes can be detected because they will manifest somehow in this variance. And many of the other techniques that have issues, they are only concerned with directly follows relationship and so on. So they will not be able to capture, for example, long-term dependencies. But we will also now see what the issue is with that in Earth Mover Systems. It's very slow. We see here it's like a logarithmic scale on the y-axis, and Earth Mover Systems is the slowest techniques of all, while LCDD and RINS are very fast, but they are exactly doing that. They have they use the directly follows relationship. And then we can look at the parameter sensitivity. So we see that actually Earth Mover Systems is very easy to use because you don't really have issues with parameters. But again, we see for LCDD, for example, there's like a huge spread. So you have to be quite careful with which parameters you choose. And then on the last evaluation goal, there's the robustness. So we see that actually two interesting things. So many techniques improve their performance with noise. So because kind of like the thought of having noise is really much factored into the design of the algorithm. If noise is added kind of like as additional events that are not fitting to the initial process model, then some techniques have huge issues. For example, RINF can detect no changes anymore, which is a huge drawback for the practical application of that technique. And based on these, like now very quickly discussed insights, we have like the following main conclusions. So first of all, there's no one-fits-all technique. For EMD, it doesn't really have a drawback when it comes to the quality of the results, but it's very slow, so slow that it probably can't really be applied in a real-life setting. But on the other hand, the highly scalable techniques, they have systematic issues with respect to certain change types and robustness to noise. So how are we moving forward based on this in the future? We see that actually incorporating variant analysis can be very effective based on EMD. So what could be really good is if we would have a faster way to compare the distribution of variance between two windows faster than Earth Mover Systems. And on the other hand, if you think back about this classification of techniques, and there was like multiple hypothesis testing, and so far that was kind of missing from process mining, what could be a really good option is to take multiple of these fast but not as good classifiers and use them in a kind of ensemble to then have like a fast but much more robust classifier that can also cover more change types. So this would be the like two main directions in which we could move process concept drift detection. So thank you very much for your attention. If you have any questions, you can reach out to me via the provided link. Thank you so much.